Alright guys, what's up? Mr. Schwarman here. Going to be talking in this video about how we can use MDSolids for beam deflection. So we're going to be working on the same problem we've been looking at in some of our other videos where we're looking at this 2-inch by 2-inch steel bar spanning a 3-foot long gap with a 215-pound construction worker standing in the center. So we've sketched it out here. It's 3 feet long, also known as 36 inches. We found the E, the modulus of elasticity, the Young's modulus, by researching the modulus of elasticity for steel. So you have to do this on one of those research websites. We also here already found the IXX, the area moment of inertia, by using the 2 by 2 BH cubed over 12. So those are things that you have to have already done or know. You need to know the E and the I if you want to be able to use MDSolids, along with things like the length and the force. So we're going to be going back and forth between our setup and MDSolids and make sure we get the same answer we got mathematically using the equation. So to MDSolids, what we are talking about is a determinate beam. So I'm going to click on this one. And it is supported with two ends. It is not cantilevered, which is what these two are. So I'm going to click on this one. The total beam length. Now I'm going to keep everything in inches like I did here. You could change it to feet or meters, but I'm going to keep it in inches. So if it's 3 feet, I know that's 36 inches. And then left and right support. What it's talking about is if you think about like an XY coordinate axis, what are the X coordinates of the left support and the right support? So if it's supported all the way at the ends, the left support is at 0 and the right support is at 36. Like those are the X coordinates at 0 and 36. So I'll say enter, and now I've got my beam defined and I can see it here. It's supported at one end A, one end B, and it's 36 long. Now I've got to add a load to it. I do that by pressing these arrows. Now I can do point loads, or I can do distributed loads, or I can do changing distributed loads. But I'm just going to do a point load because we're saying this is a construction worker in the center of the beam. So I'm going to add a downwards load. The X coordinate, if it's in the middle, I'm going to say 18 because that's half of 36. This is from the left, right? So if it was 4 inches from the left, I would put 4. 10 inches from the left, I'd put 10, etc. But since this is right in the center, I'll put 18. The load magnitude, how big is it? 215 pounds. So again, that's from the problem. We already identified it. Inches, pounds, keep our units consistent. Hit enter. Now we get this stuff and we get what's called a load diagram and a shear diagram and a moment diagram, which are all cool. These are all good, but we're going to use this for something else called deflection. And the way we're going to do that is we are going to go to options and we're going to specify the flexural stiffness. So remember, flexural stiffness is this combination of the E and the I. It's literally just E times I, and it combines those two aspects of the beam. It's material E and it's geometry I. So I'm going to click on this and I get a pop-up here. And I got to be really smart and pay attention to my units here. The default units are kip, inches squared. A kip is a kilopound or 1,000 pounds. It might be easier to do pound inch squared. So I'm going to change to pound inch squared. And here's what I got to do a little bit of math. So I'm going to put this away. I'm going to come back here. So my E is 29 times 10 to the 6 psi, pounds per square inch. And my I is 1.33 inches to the fourth. So I'm all in pounds and inches. That's why in my MDSolids I just did pounds and inches. I'm going to pull up just my computer's calculator here. And here's what I'm going to do, if I get this out of the way, is I'm going to do, and now this is not right now as like, this is a standard calculator, so it's going to be a little awkward, but we'll make it work. 29 times 10, I don't even know how you do to the 6th power on this calculator. Oh my gosh. Is there a way to make this? Here we go. Well, not an actual graph. Scientific, is this what I want? Yeah, this will be better. All right. So 29 times 10, that's not what we want. I'll figure it out. 6 to 10 to the 6. Okay, that's an awkward way to do it, but that times 29. So sorry, this is me figuring out the calculator here, but this is the E, the Young's modulus, 29 times 10 to the 6. That's this number. Times the IXX times 1.33. So the EI, the flexural stiffness or flexural rigidity here, by multiplying the E and the I, is 38,570,000 pound-inch squared. So I'm going to pull MDSolids back up. I'll move my calculator here, and I'll just type that. Oh, I can't make it pop up over, maybe if I put it here. 38,570,000. 38,570, 1, 2, 3. Just make sure, I did 1,000, 38, okay. Okay. And now this stuff changed. And now we have a slope diagram and a deflection diagram. And what's neat here is we've got to learn to read this. But if we look here at the center, this is the maximum deflection. That's what this shows, which makes sense because that's where the construction worker is standing. And if I look at this, I get a negative number. Makes sense because it's deflecting down due to the downward force, 0.00541. And if we go all the way back to our problem here, that is what we got the first time when we did the math. MDSolids is using the exact same equations and doing the exact same math that we are. We're just inputting the givens and it does the math without us typing this all into our calculator. Whereas, as we saw with fusion, fusion is actually simulating it. It's putting into a physics sandbox and simulating it. So whether you do MDSolids and you do this equation, or whether you do fusion, there are multiple ways to check and confirm your beam deflection, and this is one of them. So I hope this helps.